The speaker is Takashi Takebe from BIMSA. He will know expert on the wave equations and integrable hierarchies. He will give a talk on multi-component Toda lattice hierarchy. And let's welcome our speaker today.
Thank you for coming. This is work with Anton Zabrov in Moscow. And I forgot to write this information in the first page. So this is to appear in Russian Mathematical Surveys. Well, first let me review the old story of Toda lattice, not hierarchy, Toda lattice itself. It is one of the most fundamental systems, integrable systems, and which was found by Morikazu Toda in 1967. This is it, and this is the unknown function, and the t is time variable, and s is integer, discrete variable. And Toda found this system in search of integrable, namely a system with exact solutions written in elliptic functions. And he used many additional theorems of elliptic functions and found this system. And later, it turned out that this is quite a rich system, as we shall see. And soon after his discovery, algebraic geometric solutions, written in theta functions were found, and also solitary solutions were found. And this system is so fundamental, and it is a sort of experiment field for many solving methods. For example, Hamilton-Jacobi theory, or Vector transformations, or Hirota's binary methods, and so on, some of them. And also, after that, many contributions, mainly from Soviet Union, found. First, Bogoyavlensky generalized this system. Namely, in this system here, there is a difference of phi s and phi s minus 1. And it is a sort of A-type simple root action. And by changing, by replacing this part by simple roots of other Lie algebras, Bogoyavlensky found many generalizations. The other generalization is adding another independent variable. So this is a two-dimensional system, and often called Toda field. And also another generalization which is related to this talk is multi-component version. Namely, if we replace this exponential function of phi st as a group element and consider it as some function, and then, let me make this Toda field multi-component system. Then, well, yeah, this E5S is replaced by some group element, in this case, matrix bound function. And then we have such a term here, such this difference term becomes this. And well, yeah, the left-hand side is just as like this. So this also has nice solutions. And as I told you, yeah, such kind of term can be considered as a simple root. So Riemann and Semyon-Shansky generalized it to the groups, say. And well, yeah, I said that Toda lattice is one of the fundamental integrable systems. The other fundamental integrable system is KdV equation. Here, if you ignore this part and put this contents of parentheses to 0, then it is the KdV equation. Or it's two-dimensional generalization is called KP, Kadmon-Sepet-Viesvili equation, and which is also very important in integral systems. And in 1980, Sato in Kyoto had infinitely many independent variables, actually, which correspond to infinitely many conserved quantities, but well, yeah, it's not, the conserved laws will not appear in these talks. And well, yeah, what he defined is called the KP hierarchy. And it is infinite many equations for infinite many unknown functions with infinite many independent variables. And what the most important discovery of Sato is that the solution space corresponds to infinite dimensional Grassmann manifold, which explains the integrability in some sense. And later, soon after his discovery, that Jimbo, Kashiwara, and Miwa constructed general solutions for this KP hierarchy using some algebra, so Clifford algebra, or in physics terms, Pyrrhic fermions. And well, yeah, from this viewpoint, infinite dimensional symmetry of the KP hierarchy becomes clear. Okay, and well, yeah. So what is the combination of this Sato's story and the story of Toda lattice? Well, it's natural to consider Toda lattice hierarchy, and it was defined by Ueno and Takasaki in 1984. So well, yeah, almost the same as the KP hierarchy, but the difference is that the Toda lattice hierarchy is differential difference equations compared to differential systems of KP hierarchy. And well, yeah, the lowest degree equation, non-trivial equation, is the two-dimensional Toda lattice. This one. Okay, and the fermionic or algebraic solution of KP hierarchy naturally generalized to Toda lattice hierarchy by the three groups independently. Well, so this is Toda lattice version of KP hierarchy, but one thing is still lacking. What is the multi-component version? Can we replace the unknown function by matrix? Well, actually, yes, and that is our motivation. But of course, when and Takashi knew that such a system should exist, and actually in their paper, in the first paper, they defined multi-component system as well. But strangely, their theory of multi-component hierarchy is quite unsatisfactory from our viewpoint. Yeah, they impose some not natural assumptions, and proofs are not complete or not correct, I would like to say. And there is several insufficiency, like and they did not prove the existence of the functions, or there was not fermionic description, and so on. So our goal is fill these gaps. And the system, the Toda lattice hierarchy, or the KP hierarchy itself is already some large system with infinitely many blah, blah, blah. And Toda lattice is somewhat twice as large. And n component of the lattice hierarchy is n times 2 times infinite independent variables and so on. So sorry for this bulky description. As I said, there are 2n infinite sets of continuous independent variables. So this both T1 is actually T11, T12, T13, etc. And there is some T bar variable, which, actually in the two-dimensional lattice, there was two variables, x and y. In the Toda lattice hierarchy, T corresponds to x, say, and T bar corresponds to y. And we introduce n discrete variables. And these are usual notations. Diagonal matrix units is named. It's just. Like this is and one is of course unit matrix, and we use this notation for shift operators. Well, if you shift alpha variable, then we like like this. So this plus one is this one alpha. And so if we multiply all of these operators, then this becomes such a parallel shift operator. And all unknown functions are encapsulated in several matrix-valued difference operators. This L bar, U alpha, and U alpha bar. And also, there is some P alpha or Q alpha, which are equivalent. And this is their difference operator, shift operator like this. And with shift 1 minus j here. This is shift by j minus 1. And unknown functions are these bj, b bar j, u alpha j, etc. And I omit t dependence here since it is too much. And there are several algebraic conditions which these operators should satisfy. These commutation relations and U alphas are actually idempotent operators. Namely, if you multiply U alpha and U beta, then it is U alpha itself or zero. And sum of them, all of them is equal to the unit matrix. And these the product of all of Q's, well, Q's commute itself, so with themselves. So this product is just a commutative product, and it becomes L inverse, and product of Q bar is L bar, etc. And this is probably the most non-trivial relation. Actually, if you rewrite this relation in terms of P operator here, well, Q is almost parallel shift operators, but except for one factor. This is shift of S alpha, just one variable, and others shift all of these variables parallel. And actually, if you rewrite this maybe non-trivial strange relation in terms of p's, then it is nothing but a sort of Fourier decomposition of such product. Well, P alpha contains only negative shifts, while P bar contains only positive, non-negative shifts. So this is a sort of Fourier decomposition. Actually, such product might not exist because these are infinite series. So for mathematical argument, this condition should be taken. And so at last we come to the differential equations. which is encapsulated in this form. These are, this is for T alpha n, this is for T bar alpha n. And they are Lax equation, so-called Lax equations. Differential is commuted. And T alpha n corresponds to B alpha n, which is defined in this way, where here non-negative means we take just non-negative part of such sum. And T alpha bar n corresponds to B bar alpha n, which is constructed from L bar and U bar in this way. So we impose these Lax equations for all operators, that's L bar, U bar, Q bar. So all of this, namely these algebraic conditions and these differential equations define the multi-n component Toda lattice hierarchy. Actually, sorry. I said that these equations are algebraic conditions, but if you use P alpha or P bar alpha instead of Q and Q bar, then these, for example, this equation can be interpreted as the difference evolution of L operator in terms of P. So the difference evolution is included in these algebraic conditions. And for one component theory, because of, for example, this condition, Q alpha is redundant, Q alpha bar is redundant, U alpha is also redundant, and so on. So it is much more compact. And here the difference with this system defined by Ueno and Takashi is that they considered only one discrete variable instead of these n variables. And probably, I guess that this is the reason why they couldn't introduce tau function for this. Anyway, correspondingly, they didn't use these Q alpha. And maybe if you know KP hierarchy, the theory of KP hierarchy, this kind of Lax equations can be rewritten as differential equations for B operators like this, which is called the system of Zakharov-Shabat equations. Okay, and the rest, if you know the theory of KP hierarchy, then the rest of the this talk is almost parallel to that theory. Namely, first we linearize the hierarchy by introducing so-called wave operators. Which is a shift operator. And for example, L bar, L was an operator of this form, namely sorry, zero up. Such a difference operator. And we require that this operator, this form is rewritten in this way. Namely, this simple trivial operator is dressed by this W and W inverse as an interaction of W to get LS. Similarly, L bar is of this form, L bar is of this form. And yeah, where W bar is something like this. Well, as you see, this is diagonal matrix, diagonal operator, and this is from 0 to infinity compared to this from 1 to minus infinity, like this. And this is from 0 to infinity, and so on. So the structure of W is a little bit simpler than L and other operators. And we can show that this linear, you say this is linear with respect to W's. Linear system is equivalent in a sense to the Toda lattice hierarchy. Namely, for any solution of the n component lattice hierarchy, we have these operators. And instead, conversely, if we have W's, and if we define L bar, blah, 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 in this way, and they satisfy this equation, then yeah, it is our solution of Toda lattice hierarchy. Yeah. Yeah, well, yeah, it should be non-trivial. Okay, yeah, here it is. Yeah, the only condition is that this top term is invertible. No, it actually this is usually not invertible. And namely, this corresponds to so, yes. This is something like, yeah, maybe I'm wrong. The sign might be different, but it is essentially this function in one component case. So the Toda lattice itself is contained in this first term, Gizer box, sorry. And well, yeah, W's are operators, but But by acting, by letting them act on such a diagonal matrix, diagonal function in this way, then we have differential difference equations, linear differential difference equations for these matrix functions. Yes, and here I wrote only psi, but psi bar also satisfy the same equations. And this is some notations. We define adjoint operator for this difference operator. This is multiplication by some function, and or in this case, matrix function. And this is shift by S alpha. And then adjoint operator is defined in this way. And we define adjoint to a function using adjoint action of W's and W bars. Then one key point of the KP theory is that this psi bar, psi star bar, the adjoint wave functions, satisfy such a bilinear equation. And this is, here we write integral, but please consider it formally. Namely, we are taking residues in the product of this with respect to z. Namely, take the coefficient of z inverse. Then they are equal. Of course, you can rewrite these equations using these coefficients, but it's rather messy. So this is some compactified notation. And so KP, n component to the lattice hierarchy gives our matrix solutions of this bilinear equation. And conversely, if you have these four matrix functions satisfying this equation, then we can restore these W's by just taking, coefficients to define W in this way, and so on. So, and these W's give the n component, the solution of n component to the lattice hierarchy by this equation. And one of the big achievement of Kyoto School in 80s was the discovery of tau functions for integral systems. And for the n component to lattice hierarchy, which we define here, has also tau function like this. And I'm not good at being taken pictures. Sorry for this. And there is a matrix function tau with indices alpha, beta, but diagonal elements are the same. And these wave functions and adjoint wave functions have the elements of wave functions and adjoint wave functions can be simply expressed in terms of these matrix elements of tau function in this way. And conversely, if we have corresponding bilinear equation for tau function, corresponding, this is it. If there's a tau function satisfying this, then we have the solution of n component to the lattice hierarchy. So, okay, and this is just a notation, but we have to, when we recover wave functions from tau functions, so we have to shift independent variables like this, where this bracket is something like this. Okay, anyway, that's some small detail. Anyway, the main point is that the n component to the lattice hierarchy, that large nonlinear differential difference equations is equivalent to these bilinear equations. And as I told you, that Ejimbo Kashiramir found algebraic description of the tau function of the KP hierarchy. And the same story goes for its n component to the lattice hierarchy as well. Well, here we define a clipboard algebra in this way. They satisfy usual anti-commutation relations. And the Fock space is defined usually, namely, it is generated by just one vector, and half of these operators kills this zero. Similarly, we need right module of this algebra, which is called dual Fock space. And the pairing is defined as usual by normalization 0, 0 is equal to 1. For example, if we have only one element here, sorry, I to define the notation. If we apply some operator to 0 and take pairing with 0 here, then we write just A. So this is one of that. Any of these generators of the Clifford algebra gives this 0, right 0 or left 0. So such combination, such inner product such is equal to 0. And if we put two of them, then it's also 0. But if we put psi and psi star, then it might be 1 because of this anti-commutation relation. And we define some vector defined by these generators acting on this vacuum zero vector. And we also need certain bilinear product, quadratic, product of psi and psi star in this way. Here, black dots are so-called normal ordered product of the operators defined in this way. And so if we put such a Lie group element, well, yeah, you can consider this combination as a Lie algebra element. Namely, if we take the commutator of this kind of elements of the Clifford algebra, then we again get the same kind of psi star, sum of psi star size because of these commutation relations. So we can regard this as some Lie algebra element, and exponentiating it, we get some Lie group element, a sort of. Of course, this is a sort of very rough notation, because if we put the general sum, then it will show diverge. Also, we need some convergence relation, but convergence constraints. But yeah, I omit that. Because the main point is that if we define such an element, then it satisfies such a bilinear relation. Well, namely, if we ignore G here, then we have sum of tensor product of psi and psi j in this case too, in the right hand side too. And in the left hand side, G tensor G is multiplied from right. And in the right hand side, G tensor G is multiplied from left. And by the computation relation, we can prove that such kind of equation. Of course, we have to interpret such exponential of infinite sum in some good way. Anyway, yeah, we have such an equation, and if we put this kind of tensor on this side and this kind of vector on this side, then we have some equality of functions of S and T, and S prime and T prime. And it is, of course, bilinear, because of this. If we consider such kind of combination as a function, then this equality becomes a bilinear equation for such kind of functions. And this is exactly the bilinear equation for the tau function of the n component Toda lattice hierarchy. Well, yeah, this kind of messy prefactors come from this kind of product and commutation relations. So it's not essential, but the main part is this G, and it's dressed by such vector and such vector. Yes. Okay. This one. Yeah, well, in this case, yeah, it is a number. Yes. Of course, as I told you, we have to make some, require some convergence conditions. But for example, yeah, only finite terms might survive, but still this function is non-trivial. Yes. Yes. Yeah, exactly. Yeah. For example, yeah, for the KP hierarchy, I told you that it is the solution space is essentially infinite dimensional Grassmann manifold, and Grassmann manifold is explain. Sorry. Matrix factor of GL by this kind of matrices. And for Toda lattice case, this GL itself becomes, in a sense, up to some convergence relation, convergence requirements, conditions, GL is the solution space. And in the n component case, this corresponds to this GL. And so, yeah, yeah. So essentially that, and as I told you, we published this last year, and it will soon be published in Speak. And well, yeah, that seminar paper by Ueno and Takasaki is this one. And this is also the fundamental literature for the KP hierarchy. But the idea, all the idea is already in these papers. Thank you.
So, do we have questions? Okay, let me ask you. So, can you write kind of linear Hirota equation in this case in terms of this Hirota derivative, which differential equation can be solved one by one?
Yeah, I didn't try, but from this kind of bilinear equation to Hirota bilinear Hirota differential notation is somewhat standard. So probably, yeah.
Yeah, so from here you can obtain easily like 3 terms Hirota equation.
3 terms Hirota equation is for Toda lattice, right?
Yeah.
Yeah, and yeah, I don't remember. Probably I have not yet tried, but it's quite standard. It should be.
Have you tried to derive one Sultan solution in this case?
What solution?
One Sultan.
Once and never. Sorry.
Okay. Another questions? No? Okay, let's thank the speaker once again. So our afternoon session is finished. See you next day.